Welcome back from the break, everybody. The next speaker is Colin Defant from Harvard, and he's going to speak on the triangular grid billboards and Plabic graphs.
Yes, billiards. Okay, yeah, oh, well, this is kind of loud. Is that okay? Should I? Okay, so it sounds loud to me. Thank you, everyone, for coming, and thanks to the organizers for putting all of this together and for the chance to speak here. This is based on joint work with Pro Geratolock. So I was talking with Teo a couple days ago, and I said that I appreciated the jokes in his talk, but that I didn't plan any jokes for this talk. And he said, well, you've been writing so many papers with Nathan Williams that should probably make up for it. And then I said, well, yeah, at this point, basically my whole career is a joke. And this was before the poster session. So anyway, then he said, well, you could use that as the joke in the talk. So, well, here we are. That was the joke. And there are no more jokes in the talk, so the rest is going to be totally, completely serious, except not really. I think it's pretty fun. So the setup is we're going to take the infinite triangular grid, and we're going to draw a polygon in this grid. And we'll assume that it's simply connected, so there are no holes, but it doesn't have to be convex. And we're going to assume that the boundary is made out of these little edges in the triangular grid, and I'll label those edges as B1, B2, B3, and so on, going around clockwise. Now I'm going to start at one of the midpoints of these boundary segments, let's say B1 there, and I'll shine a beam of light so that it makes a 60-degree angle with that boundary segment, and I'll shine it down here, in this case in the southeast direction. It's going to travel and hit B3, and then it's going to reflect off like it hit a mirror, and it'll travel over and hit B32. Then it's going to reflect off and travel down to B sub 26, and then reflect off to B6, and so on, and it'll trace out this green path that I've drawn here. I'm going to call this one trajectory. So notice I would have gotten the same trajectory if I had started at B2, or B3, or B4, but if I start at B5, I get a different trajectory, namely the one that I've drawn here in blue. And if I start at B7, I get this purple trajectory. And if I start at B8, I get this red trajectory there. So this is what I'll call the billiard system of the polygon, and it has 4 trajectories. You can also think of this as giving a permutation. I'll call this the billiards permutation of the polygon. This is just the permutation that sends I to j if the beam of light travels from the midpoint of bi to the midpoint of bj. So here I've written the cycle decomposition of this permutation that you would get, and there are 4 cycles corresponding to the 4 trajectories. So the main question that we were asking was basically how big does the polygon need to be relative to the number of these trajectories? So it's a kind of extremal question. And you can measure how big the polygon is in 2 different ways. You can say, I could look at the area. And when I talk about the area, I'll mean the number of these little unit triangles inside of the polygon. So we're just normalizing the area so each little unit triangle has area 1. Or I could talk about the perimeter, which I'll just mean the number of these little boundary segments. So in this case, that would be 33. Well, so the main result we prove is that the area of P is at least 6 times the number of trajectories minus 6. Now, I'm writing sec of P for the number of trajectories because it's also the number of cycles in the billiards permutation. And we also show that the perimeter is at least 7/2 times the number of trajectories minus 3/2. Now, the area result here is tight, and we show that the area is equal to 6 times the number of trajectories minus 6 if and only if the polygon is what we call a tree of unit hexagons. It's basically something that looks like this, where you take a little regular hexagon of side length 1 and you glue it to another hexagon. You just keep gluing it to form like a tree. It's not hard to show that these do attain equality here, because every time you add on a little hexagon, you're going to increase the area by 6, and it's not hard to show that you increase the number of trajectories by 1. The difficult thing is showing that these are all of the equality cases and that this inequality is always going to hold. Now, the perimeter result is not tight, and we conjectured that the perimeter should be at least 4 times the number of trajectories minus 2. So I was going to state this as like the big conjecture that we were hoping someone would solve, but now I think someone solved it. So just last week, one of my students at the Duluth REU program, his name is Honglin Zhu, he claims to have solved this. I haven't actually seen it written up, but the advisors there tell me that it seems correct, so I'm very excited about this. He's very good. We gave him multiple problems, and he solved them, and we were like, okay, let's give him something like really hard. And we thought this would be really hard, but then he did it. So he seems very good. Anyway, the equality cases here are weirder. It's not just these trees of unit hexagons. Here, there are two examples. Each one of these has 5 trajectories in the billiard system, and each one has perimeter 18, and well, 18 is 4 times 5 minus 2. Okay, so yeah, it's just the equality cases are weirder. So I guess that's basically what I wanted to talk about in terms of results, but for the rest of the talk, I'll tell you about the motivation for how we came up with this setting. I think it's sort of a natural thing to consider on its own, but we were led to this from Plabic graphs. And then I'll state a bunch of open problems. Okay, so Plabic graph, well, we saw this in the last talk. It's a planar graph embedded in a disk so that every vertex is either black or white. So Plabic means planar bicolored. And okay, here's an example of a Plabic graph. Now, I'm also going to assume that there are these marked boundary points on the boundary of the disk. I'll call them B1 star, B2 star, and so on, going around clockwise. And we'll assume that each marked boundary point is incident to a single edge that connects it to one of the vertices in the graph. So this is also part of the data that goes into the Plabic graph. It's like the graph inside, but then also the marked boundary points and these extra edges. So these are important for a variety of reasons. As we saw in the last talk, they show up in studying things like the totally non-negative Grassmannian and the amplitahedron. But we can also study them just from a combinatorial point of view. And we can consider a combinatorial construction that Alex Postnikov came up with. So he invented these Plabic graphs, and he also defined the trip permutation of a Plabic graph. So what we do here is we're going to start at one of the marked boundary points, let's say B1 star, and we're going to follow the edge that's incident to it until we hit a vertex. And when we get to a vertex, we're going to follow what are called the rules of the road. So the rules of the road say if you hit a black vertex, you turn right, and if you hit a white vertex, you turn left. So in this case, I hit this black vertex, and okay, you imagine you're kind of facing down, so you turn right, so that would be this way. So then you travel over here and you hit this white vertex, so you turn left. And then we hit another white vertex, so we turn left. Then we hit this black vertex, so we turn right. Then we hit a white vertex, so we turn left. And we end up at B3 star. So what I've drawn here in red is the trip starting at B1 star, and you can see it ends at B3 star. Similarly, I drew the trip that starts at B5 star. That's here in green. It ends at B2 star. There will be one trip for each one of the starting points. I just didn't draw them all because it would clutter the diagram. But anyway, this gives you a permutation. And it's just defined by saying that the permutation should send I to J if the trip starting at BI star ends at BJ star. Okay? So in this case, it would be this cycle that sends 1 to 3, 3 to 5, 5 to 2, 2 to 4, and 4 back to 1. So the reason this is related to what I was saying before is because if you have one of these triangular grid polygons, you can get a Plabic graph from it by basically doing a dual graph construction. So you're going to put a little vertex inside of each one of the little unit triangles, and we'll color the vertex black if the triangle is right side up, and we'll color it white if the triangle is upside down. And then if you have two triangles that share an edge, then you'll connect their vertices with an edge. And then we also draw these extra edges coming out of the boundary segments here. Those connect with these marked boundary points. And the point of this is that the trip permutation of this Plabic graph is the same as the billiards permutation of the polygon. This is not hard to convince yourself that this is true if you sort of stare at an example for a minute or two. For example, here, the trip permutation sends 5 to 9 because the trip starting at B5 star will end at B9 star. But also in the billiards permutation, 5 goes to 9 because the beam of light travels from B5 over to B9. Okay, so this is really what led us to consider these billiard systems of polygons in the first place, but then you could say, well, what led us to consider this family of Plabic graphs that come from these triangular grid polygons? This was coming from a paper by Thomas Lamb and Alex Postnikov, where they define these objects called membranes. I'm not going to define membranes formally, but basically they're these triangulated surfaces in some Euclidean space. And if you have one of these membranes, you can get a Plabic graph from it. And basically, this is, again, doing some dual graph construction, where you put a little vertex inside of each of the triangles in your triangulated surface. You color it black or white according to some rule. And then if you have triangles that are next to each other, you connect their vertices with an edge. So you get this map going from membranes to Plabic graphs. Actually, what you get out is a reduced Plabic graph. I won't define reduced, but this is sort of the nice family of Plabic graphs that you might be interested in if you're concerned with something like the totally non-negative Grassmannian. So this actually gives a surjective map from membranes to reduced Plabic graphs. And one way you can think about this is if you have a reduced Plabic graph, then the membranes mapping to it under this map are giving sort of geometric realizations of that Plabic graph. And this motivated Lamb and Postnikov to define what they call the essential dimension of a reduced Plabic graph. It's just the smallest positive integer d, such that there exists a membrane in d-dimensional Euclidean space that gives such a geometric realization. So it's kind of like a geometric measure of the complexity of the Plabic graph, because it's saying you have to go into at least this many dimensions to find one of these geometric realizations. Okay, so what they showed, this is the main thing they showed about these essential dimensions, if you have a reduced Plabic graph with n marked boundary points, then its essential dimension is at most n minus 1. And they also characterize the equality cases, so they show you get equality if and only if the Plabic graph is parametrizing a top-dimensional cell in the totally non-negative Grassmannian, and you can characterize those in terms of the trip permutations as well. But anyway, we said, okay, well, they've understood the maximum possible essential dimension. What about the minimum possible essential dimension, namely 2? And, well, I'm going to assume connected here. That's not really a big deal. The connected reduced Plabic graphs with essential dimension 2 are exactly those that you get from this dual graph construction with the triangular grid polygons, and that's kind of just by definition, because these triangular grid polygons really are just membranes in two-dimensional space. So kind of by definition, this is the family of Plabic graphs, and that's sort of what led us to consider these. Okay, so this means that we can reformulate our main result in the language of Plabic graphs. We can say, suppose G is a connected reduced Plabic graph with essential dimension 2. Let's say it has n marked boundary points and v vertices, and let's let C be the number of cycles in the trip permutation. Then V is at least 6C minus 6, and N is at least 7/2 C minus 3/2. And then if you take this recent result of Honglin Zhu, that would say that N is at least 4C minus 2. Okay. So those are, that's sort of the motivation that we had, and I guess in the remaining time, I don't know how, whatever. In the remaining time, I'll just mention some open problems and further directions that I think would be interesting. So one thing you could do is look at other families of Plabic graphs. So on the previous slide, I said, well, we have these connected reduced Plabic graphs with essential dimension 2, and we get these inequalities relating the number of vertices or the number of marked boundary points to the number of cycles in the trip permutation. You could say, well, what if you do this with some other interesting family of Plabic graphs? For example, you could look at connected reduced Plabic graphs with essential dimension 3, or maybe you have your own favorite family of Plabic graphs, or maybe you could do something with a grid like I've drawn here, so you can draw some other grid besides the triangular grid and say, okay, I'm going to draw a polygon in here and do a kind of dual graph construction like we did before. This will give you some family of Plabic graphs, and you could again try to get some inequalities here. Anyway, I haven't really looked into this, but maybe that could be an interesting thing to do. You can also look at regions with holes. So at the beginning I said, let's assume our polygon is simply connected, but what if it's not? So here's an example where this area inequality that I wrote down fails, and that's because there's this hole here. And you could say, well, maybe we could get some kind of inequality relating the area with the number of trajectories, but maybe it has to take into account the genus, for example. Right? Maybe you can refine the inequality to take this into account. One thing that I think would be really cool is to get something along the lines of if you have a large random triangular grid polygon, or maybe it doesn't have to be a polygon, maybe just some region, maybe it's not even connected, and you do this billiard system, you just define it just as before. You can say like, okay, what would you expect the number of trajectories to be? Or maybe there's something interesting with the variance. I kind of expect the variance of the number of trajectories would be big in the sense that like probably this should be sensitive to what happens on the boundary. But anyway, this is, I would personally love to think about this if anyone has ideas. Part of the issue is just figuring out what is the correct model for a large random region that you should be using. So anyway, I think that would be cool. Let me know if you're interested or if you have ideas. Another thing you could do is look at polygons such that there is exactly one trajectory in the billiard system. You could say, okay, how many of these are there, for example, or maybe get some kind of asymptotics for the number of these if there's not like a nice exact formula. And then finally, let me mention, so this is a suggestion that Nathan Williams gave me. Let me see, yeah, okay. And I'm going to go kind of quickly through it here, but it's written down more formally and precisely in our extended abstract. So if you want to look at it there, that might be a better place to digest things, or you can ask me about it. So I'm going to fix a finite set P of alcoves in the affine Coxeter arrangement of type AD tilde. Okay, so this is like an affine symmetric group. And I'm going to let S0 through SD be the simple reflections in this Coxeter group. So the Coxeter graph is basically a cycle, and it has S0, S1, S2, and so on listed around clockwise. Okay, now I can identify the alcoves with the elements of this Coxeter group. There's a way of giving a one-to-one correspondence. And so if I have one of these alcoves in my set P, and I have some j in Z mod D plus 1Z, I'll define tau j of W to be, well, I want it to be Sj times W if Sj times W is still in my set P. Otherwise, it's just going to be W. The point of this is when you multiply by Sj on the left, you're going to just move into an adjacent alcove, and I'm saying move into that adjacent alcove unless doing so causes you to leave the set P. In that case, just stay where you are. And so now just do this sequence of these toggle operators. Do tau 0, then tau 1, tau 2, and so on, all the way to tau d. Then just rinse and repeat. Do tau 0, tau 1, tau 2, and so on. And let me show you what this is doing in the case of d equals 2, and that'll sort of illustrate why I'm doing this. So in the case of d equals 2, the alcoves are really just the triangles in this triangular grid. So you have to mod out by like the span of the all ones vector, but let's ignore that. So these are your alcoves, and let's say I take P to be the set of alcoves in this hexagon that I've drawn here. So this in here, that's P. And let's say I start at this alcove here. So I'm going to do tau 0. Now tau 0 says try to multiply on the left by S0. And if I do multiply on the left by S0, I would move into this alcove here. And so that's still in my set P, so I'm going to just move there. Then I say, OK, I'm going to do tau 1. Tau 1 says try to multiply on the left by S1. And doing that would move me into this alcove, which is still in my set P, so I move there. Then when I do tau 2, it's going to move me into this alcove. Then I do tau 0 again, that moves me into this one. Then tau 1 sends me here, tau 2 sends me here. Now I want to do tau 0 again. So tau 0 says try to multiply on the left by S0. If I did that, I would move into this alcove down here, but that is outside of my set P, so I don't want to do that. So I just stay put. So I have this little loop saying just stay where you are. Then I do tau 1 again, but tau 1 now says let's multiply on the left by S1. That'll move me into this alcove, so I do that because it's in P. And then I do tau 2, tau 0, tau 1, and tau 2, and I just keep going. And you can see we're basically reconstructing this kind of billiards thing. So this is actually going to behave the same way as the beam of light. It's just going to bounce around. In this case, I think it would form a triangle, but you get the billiard system again. But the point is this formulation makes sense for any d. It doesn't have to be d equals 2. And you can ask the same kinds of questions. You can say, can we get some kind of inequalities relating the number of trajectories that you would get, define it in sort of the obvious way. Or actually, we give a definition, like in our extended abstract, of exactly what a trajectory should mean. And compare this with something like the number of alcoves in the set P. That's sort of like the area that we had in the case of the polygon. But maybe this P, you might want to put conditions on it. Maybe it has to be simply connected. Maybe it has to be, I don't know, convex or something. So anyway, I think that is all that I have to say. I went a little fast, but OK. There we go.
I was going to say questions, but there's one right.
Oh.
So can you characterize the permutations you can get from the process?
So the question was, can I characterize the permutations that you get? We don't do this. I think we thought about this at one point, but it seemed like it wasn't some nice characterization. That's not to say it's impossible. I think we were thinking about that, and then we kind of moved into this more extremal direction and said, OK, let's focus on this. Yes, Sam?
Do you have this special class of Plabic graphs in central dimension 2?
Yes.
Are you aware that they also can be viewed as SL3, like irreducible SL3 webs, because they're bipartite and trivalent?
Oh, yeah, we didn't look at it from the point of view of webs, but I see what you mean. Oh, should I repeat the question? OK, the question was, am I aware that these specific Plabic graphs that are coming from the triangular grid polygons, those can also be viewed as SL3 webs? Okay.
Yeah, you might talk to the group that did the web poster.
Right.
2 days ago.
Okay. Yeah, I didn't see the web poster because I was with a hat, but.
Sorry, can I just
Yes.
to add on to what Sponsor asked about, can you read the essential dimension from the permutation of the Plabic graph?
From the trip permutation? Oh, sorry, the question is, can I read the essential dimension from the trip permutation? This, I think, is something that would be cool to do, but I don't know how to do it. Yeah, I think I thought of that at one point and haven't gone back to it. But yeah, that would be nice. Yes?
So I have 2 questions. One is there a characterization of trip permutations in general?
Oh, okay, so the question is there a characterization of trip permutations in general? I think, is it true that every permutation can be a trip permutation? Yeah, because basically these decorated permutations parameterize the cells in the totally non-negative Grassmannian, and the trip permutations give you the decorated permutations. But any permutation can be decorated, yeah, with its fixed points.
The second question is, if you constrain your regions to be convex, does that improve the inequality?
That's a good question. Yeah, I had that on my slides and then I deleted it. Oh, yeah, sorry, I have to repeat the question. What happens if we do assume that the region is convex? That would probably, I think, as you say, strengthen the inequalities. We haven't looked into that. I think I thought of that question also like a week ago and haven't done anything with it, but that also would be a good open problem. Yeah. Yes?
So when you were talking about the generalization to when things aren't trivalent, or maybe there's a grid and there's 4 valent things, when you do the trip, are you still sort of turning up, like
Yeah.
right?
You will turn maximally right or maximally left, right. Oh, I should repeat. In the case when the Plabic graph is not trivalent, what do you do in terms of turning right and left? And the answer is you go maximally right or maximally left. Yes, Yannick?
Yeah, also related to that, I guess for the square grid Plabic graph, are these related to square grid billiards?
Oh, like, you mean like in the picture that I had here? Yeah, so what you would get here is you kind of bounce around like at a 45-degree angle, so you'd kind of go like this. This particular case of the square grid, I think, is actually not hard to do, the analog of what we did with area and perimeter inequalities, but these we didn't look at. But this, yeah, I think it's not that bad, at least for the questions we were considering. Yes? Right, okay, so, okay, let me try to repeat this. So the question is basically, can you define, I guess, instead of just having a polygon, maybe you have some surface that you define by local rules where you have like a triangle and it's glued to other triangles, and maybe this doesn't have to be confined to the plane, and you can do the same thing. I think this is a good idea. I think we considered this at some point when we were trying to prove this perimeter result, because we thought maybe we have to do an induction where we end up going into that setting. But we didn't make it work. But I think this does make sense as something that you can define. You also asked if this is related to the Plabic graphs. I don't know if it would relate exactly to the Plabic graphs, but I know that there are like generalizations of Plabic graphs that people have come up with. Maybe there's something in terms of those. Yes, Christian. Mm-hmm.
Does that have connections to other invariants on, say, the matroid or positroid variety or positroid cell that is corresponding to the graph?
Right, so the question is, does the number of cycles in the trip permutation have some kind of meaning in terms of the positroids or the totally non-negative Grassmannian side? I'm not sure, I don't know. Yeah, I don't know that off the top of my head. Yes? Oh, yeah, okay, so the simply connected is definitely very necessary in the proof. Right, how does the proof go? I don't know if I know how to answer that question off the top of my head. It is crucial, but like it's basically a lot of Euclidean geometry, and yeah, I don't know how to answer this. But it is very necessary. Yes, Justin?
Yeah, so you're talking about the number of cycles that got me into another permutation statistics, and the one that's example think about is fixed points. I quickly realized, at least in the version that you had at the beginning where you have all these triangles and stuff, you can't have a fixed point. As soon as it bounces off the wall, it won't return to that wall until after it bounces off some other wall. What other cycle sizes are possible?
Okay, so the question is, what are the possible cycle sizes in a trip permutation, or I guess in a billiards permutation, I'll say. I think it should just be everything that's at least 3. Right, you can't have 2 cycles, and I'm pretty sure you can construct it for anything that's 3 or bigger.
If there are any more questions, I suggest that we leave them to the speaker later, but let's thank the speaker one more time.